Let's take a look at this problem. Due to slipping points A and B in the rim of the disk have velocities shown, determine the velocities of the center point C and point E at this instant. Remember, if there was no slipping, the instant center would be at point A. But there is slipping, so we can't assume that in this case. So let's take a look at this. So again, we're given these velocities. And this is point A here. And so remember, if we have two parallel velocities like this, and they're going opposite directions, we can usually use similar triangles, and we can maybe set them up like this. Where, like, let's say this side would be the 5 feet per second. This side would be the 10 feet per second. Like this. And the instant center will be given by making a line between those two arrowheads like this. And then the instant center will be right here. That'll be the instant center right there. And so we can use similar triangles to start figuring things out. So let's say, let's give some of these names. Let me call this X. And now since the radius is 8 feet, then the diameter is going to be twice that, or 1.6 feet. So if this is X from here to here, then from here to here must be 1.6 minus X, like this. And again, like I said, the instant center is right here. And again, we can use similar triangles to figure out these values. We could say that 1.6 minus X is to this as X is to that. So let's write that down. So in other words, 1.6 minus X is to 5, looking at, say, this triangle here. And that's going to be equal to X to 10 for this triangle. Like this. And let's see, we could cross multiply. We'll multiply both sides by 5. That'll give us 5 over 10 here. Or 0.5x. And then if we bring, let me bring this x over here, 1.6, 1.5x, then x 1.067 feet, like this. Now we'd like to find the angular velocity. And so we can use some of the information we have. So we know the velocity of B is 10 feet per second. And we know what x is, so we can use the equation velocity of b is going to be omega. And then this x would be maybe call it RB or RB with respect to the instant center. I'll just call it RB. Or like I said, a lot of times you can call it RB with respect to the instant center. In any case, we know here that that distance to that velocity from the instant center is going to be 1.067. And we know that this is 10 feet per second. So this is 1.067 feet. And so the angular velocity is 9.37. Radians per second, like that. So that gives us the angular velocity. Now we can find some of these other quantities. Now, we're going to have to relate everything to the instant center. So let's take a look at, say, for E. Take a look at E. And so E is over here. And again, the center C is here, but the instant center is below C. The instant center is down here. And so we need to find this radius right here. Maybe call this RE. So we know this distance here has to be the distance from C to the instant center. And again, the instant center is 1.67 from the top, and C is 0.8 from the top. So this has to be 1.067 minus 0.8. And so that comes out to be 0.0267. And so if we want to find this radius E, using Pythagorean theorem, will be 0.8 squared plus 0.267 squared. And that comes out to be 0.8433 feet. And then so and now we know that, again, if this is the instant center here and this is the velocity, then the velocity at E will be directed in this direction. And we know that the velocity of E is going to be equal to omega times, we call that R of E. And then the velocity of E is going to be our 9.37. Times 0.8433 that's going to give us 7.9 feet per second. That. Then finally, if we want the velocity of C itself, if we look at this picture up here, C is 0.267 feet from the instant center. Again, once again, the velocity of C then will be omega R. Let me call that just R of C. Velocity of C is going to be 9.37 times 0.267, and that's 2.5 feet per second, like that.